That was a whole roller coaster ride that I just went on with Beetlejuice.
Bunny
Went from
Hills.
not knowing what it was to feeling like a fool for not knowing it was Orion's armpit, to thinking that we are all going to possibly be obliterated at any moment, to being like, it's all going to be okay.
Probably okay.
Are we?
Yes.
Where are we?
Here.
Why are we here? Not entirely clear. We are misfits thrust into existence by random chance, with no hints at all as to how we're supposed to make sense of it all. It's immensely bizarre. Here we are.
Hello, everybody, and welcome to the Here We Are podcast. I am so excited. I am here in Las Vegas, and I had such a wonderful time. The first leg of my Vegas residency at Area 15, and getting ready to launch a big national tour and everything. And a lot of fun opportunities have come up along the way. I've met some cool people since being here, and one of them is Andrew Kerr, who is the head of the Las Vegas Planetarium.
Yep, we're the Dale Etheridge Planetarium. We just got renamed last year for the first and only other manager of the planetarium. It's been 46 years or something like that, and I'm only the second manager of the planetarium.
Really?
Yep. So my predecessor was there for 38 years.
What were planetariums like 46 years ago?
Well, actually, very similar to what we have today, with one big exception.
Don't tell customers that. Don't tell them you have.
No, it's actually okay, because the major difference, of course, is the idea of the digital planetarium versus the old star ball. So the old star projectors, which everybody tends to think of as being in the planetarium, you know, the two spheres, one on each side, and the stars being projected on the dome that way. That's one of the biggest differences. And it's not even a difference in some planetariums, because some planetariums still maintain their star balls. There are some planetarium folks who absolutely prefer the star ball look for the stars in the sky.
No one decided to call them Spaceballs?
No,
as a homage?
That would be very funny too, actually. But star balls is just what they've always been referred to, and so Spaceballs would have been funny, yeah. But yeah, the star ball has actually been around for 100 years. And so the very first planetarium opened 100 years ago in Jena, Germany. And so we're going to be celebrating this fall and into next year the 100th anniversary of the planetarium.
Planetariums.
As well.
Oh, that's interesting.
Yeah.
And how are planetariums doing these days? I mean, when was the peak planetarium? It's so interesting, because now we're here in Vegas. You have some pretty stiff competition now.
I definitely have a lot of competition. We're not a destination planetarium. That's the big difference. There are a lot of planetariums out there that are destinations. It's places that folks come to specifically to go to the planetarium. So you're looking at like the Adler Planetarium in Chicago, and down at Griffith Observatory, their planetarium there. Those are destinations. People do that. But, our planetarium, while we are one of two in the entire state of Nevada, we're not really a destination. There's not a lot of folks who come in from outside to come to Las Vegas who are coming to the planetarium.
Right.
We see a few tourists who come in because they say, oh, well, this is interesting. Hey, there's a planetarium here. Let's go ahead and go. But yeah, for the most part,
locals, people at school and stuff.
Exactly. We get a lot of locals, but we do a lot of field trips, and that's really our bread and butter, because we're attached to the College of Southern Nevada as well, and so I like to kind of think of the planetarium as an entry point for kids to come to college as well. And we have a lot of students in Las Vegas who would be first generation college students. And so getting them interested in CSN through the planetarium is one of those things that's really good for all of us.
Yeah, I had one in UWL, the University of Wisconsin La Crosse had a planetarium I'd go to as a teenager, and that's not the biggest school in the world.
No.
And so they must have planetariums all over the place at universities.
They actually do, but it's more on the East Coast.
Okay.
In the 1960s, during the space race and with the moon landings and everything, planetariums really exploded, especially on the East Coast. There were high schools and grade schools that put in dome theaters for planetariums in the 1960s, just because of that whole interest in the space race, the whole us versus them mentality of the U.S. versus the Soviet Union, and so a lot of planetariums sprung up at that time. Back at the first planetarium I worked at in Ohio, there was a school about 15 miles away, and they asked me to come in and look at what they had to see if we could get it up and running or help them do anything with it. And unfortunately, we weren't really able to do it at the time. But so yeah, a lot of schools, especially in the 60s and 70s, really pushed planetariums, and a lot of those have kind of fallen by the wayside now at this point.
And so you wrote me, you DM'd me on Twitter a while back, and it's actually, I mean, I go through long periods of time where I never check Twitter. I very rarely check my DMs on any social media. Even when I check my DMs, it's usually like there's too many things. I don't like to respond often, but. I saw it and I was like, oh yeah, absolutely.
Well, yeah, and I figured with your love of science and seeing that you were coming into Area 15 to be doing your the residency, I was like, well, this is someone I need to invite to the planetarium. I do that quite a bit. I try and find folks who are coming to town and say, hey, come over to the planetarium. And I've had a few take me up on it, but you were the fastest.
Yeah,
that's for sure. You jumped on it immediately.
Yeah, of course.
I was thrilled with it because the Here We Are podcast and everything like that. It's a marvelous thing.
So let's talk about your science background.
Okay. Sounds good.
Hit me up. What's your background?
We can start from the very beginning if you really want to, because
let's do it.
It actually started with my mom and dad. They brought home a pickup truck full of telescopes and assorted parts from an unclaimed freight store when I was about 7, 8 years old, maybe 9 years old, something like that. So I started putting together telescopes. I mean, these were the Tascos. They were the mass marketed telescopes. But we had some 3.5-inch reflectors, some 4.5-inch reflectors, some refracting telescopes. So we just kind of fixed them up, put them together. We sold a few to make back the money from how much they'd spent on the telescopes. It was ridiculously cheap. I think 77 telescopes and assorted parts for $150. and so I spent my childhood building and putting those scopes together and sighting them in, and we'd go out in the yard and we'd look at Jupiter and Saturn and all the planets, and we'd look at the stars and everything like that, and so that's really kind of where it started for me.
That is such a cool story.
Yeah.
That's one of the, you listen to the show. I love asking people's origin stories. That's one of the finest ones I've heard.
Well, it is kind of an origin story too. It's one of those things, but yeah, so my parents are really actually the ones who are responsible. And from there, it just kept going. 8th grade, I read Stephen Hawking's A Brief History of Time, which is still one of the most marvelous science books ever written.
So good, yeah.
And from there, just branching out into all of that, and that's what took me into physics. And so I started off, when I went to college, I started off as an engineering physics person. So I was taking electrical engineering classes and physics classes. And kind of after a couple of years of the electrical engineering stuff, I was like, I don't think I want to keep doing the engineering stuff, and just moved over to straight physics. And that was really what I loved doing anyway. I was always more of a theoretical guy. And so I switched over to just straight physics and never looked back. So got my undergraduate degree in physics and went to grad school at the University of Missouri in Columbia. And started working with my advisor there, Dr. Barham Mashoon. He actually, theoretical astrophysicist, marvelous in the field. Actually, the main journal was dedicated to him on the occasion of his 60th birthday.
Cool.
And so did my project that way, got my PhD by talking about the Gravito-Electromagnetic Effect, and actually adding in the Cosmological Constant. So that tells you how old that is.
I have no idea. It's been so long. I didn't read a brief history of time until I was in my early 20s. Maybe I was 20, 21 or something like that. Yeah. And I got into physics for a few years in my early 20s. Liked it a lot. And it's been so long since I've read physics. And, in the show, I've had one physicist ever. You're my first astronomer.
And I'm the first astronomy guy right now, and which actually makes me feel pretty good.
That's awesome,
and so, but yeah, so.
Yeah, as long as you don't mind me not knowing a damn thing.
No, that's okay. And I'll explain a little bit here. So the Gravito-Electromagnetic Effect it was my advisor's thing. It's also known as the Mashoon effect, named after him. What it is so in electricity and magnetism, moving charge creates a magnetic field. And that's what magnetism is derived from. Magnetism is actually solely derived from electrical charges moving. So my advisor thought, well, what if the same kind of happens with gravity as well? And so he came up with this Gravito-Electromagnetic Effect, which essentially says that the gravity we're all used to, that's pulling us down towards the center of the Earth, that makes us have to go 17,000 miles an hour to get out into space, all that good stuff. So what if that was Gravito-Electric Effect, kind of the straight line aspect? And then what if you set mass in motion? So either, like in the Earth's case, it's spinning, it's also, revolving around the sun, it's also, we're all revolving around the center of the galaxy. So with that moving mass, does that create a gravito-magnetic effect? Sort of a circular style of gravity that might exist, in addition to the straight line gravity that everyone's used to. And so basically, the thought experiment was, if you put a clock on two satellites in space and you send one in the same direction that the Earth is rotating and one in the opposite direction that the Earth is rotating. So you send them opposite directions in space. Is there going to be any sort of an effect? And it turns out there is. So moving mass does kind of create this gravito-magnetic effect as well. It's small. One orbit around the Earth is like 10 to the minus 7th seconds difference.
But if it's a satellite, that's significant.
If it's a satellite, it's significant. Exactly. And so that's the Gravito-Electromagnetic Effect in as small of a nutshell as I can get.
That's a nice, manageable nutshell.
Yeah, and so what I did is my PhD was adding on to the Gravito-Electromagnetic Effect and adding in the Cosmological Constant. So the Cosmological Constant was, at the time, what is now referred to as dark energy. So, the universe is mostly dark energy, then dark matter, then luminous matter. And so, but the dark energy is what opposes gravity, and dark energy is actually what's causing the acceleration of the expansion of the universe.
Can we talk about that a little bit? Because is this... oh boy, I am so rusty. Because the idea is that that Earth is not a vacuum in the way that we think about it necessarily, because there is this dark energy, and this is why part of the reason why we don't anticipate the universe necessarily collapsing in on itself.
Yes, that is one of the big things. because of the expansion, and the universe is still expanding. It is expanding as we speak. There are things that, yes, are getting closer together, but that's a localized thing that just overcomes the dark energy. The dark energy is pushing everything so that eventually there are folks who have done the calculations, and the last one I heard, about 100 billion years from now. So, the universe is about 13.8 billion years old right now. So give it another 87 billion years, roughly. And everything will be pushed so far apart that not even new stars will be able to form. There won't be that ability because space is expanded so much, and everything will be pushed so far apart that eventually the last star will go out and the universe will just be essentially at absolute zero.
Wow.
And so there's a lot of folks who say that the Big Crunch is probably, non-viable anymore as far as that's concerned.
Interesting.
Now, I'm sure there's probably some calculations you could make where you could say the Big Crunch is still a viable thing, and it could happen. But
you're not putting your chips on.
I would
Big
put
Crunch?
I would put my chips on ice for the end of the universe rather than fire.
Okay, all right.
Since we're in Vegas, I won't go all in, but everybody in science is always, well, I'm 99% sure.
Yeah. And so that's because wasn't the inspiration for some of Einstein's earliest ideas of relativity and everything? What wasn't that kind of about? Weren't they kind of trying to patent ether? This idea of ether at the time, trying to solve why the universe hasn't collapsed in on itself.
Exactly, the static universe. Einstein actually believed in a more static universe. He did not believe in the expansion at the time when he was working on relativity in 1906 and that time period. And so the cosmological constant was his answer to gravity. So that gravity went to pull things in, the cosmological constant pushed things apart, and they were balanced. And so he kind of believed in the idea of the static universe, and that was the way that in which he could do it. So,
okay.
And then it kind of fell out of favor once the expansion was discovered, and then it kind of came back in with the acceleration of the expansion.
Yeah.
And so and was renamed dark energy at that point. So yeah, if you
That's
hear
a lot of big changes in ideas in 100 years. Yeah.
Oh yeah, no, the last 100 years of physics have been the most monumental 100 years of just about any science.
Really?
Yeah. At least as far as going from black holes and things like that had been thought of before the 1900s. There were folks who actually had thought of them in the 1800s and actually even earlier. Dark stars that had gravity so high that light couldn't escape. There were people who actually had thought about that. But starting in 1906 with relativity, and then moving into quantum mechanics, and then when you think about the Wright brothers, even with their aircraft and aerodynamics and aeronautics and heavier than air flight, and you think about where we are today, and we've got the airplanes coming over that we're hearing, and it's almost ridiculous to think how far in 100 years we went. And actually, really, we even went that far because in 1969, the moon landing, from 1906 to 1969, 63 years, we made it to the moon. And that's, all of the physics that was developed for that was developed in that time period, that 63-year time period. It was nuts.
But we're done now. We figured it all out now.
Oh, goodness, no. You know better than that. Just
come on.
Yeah, I
what
wish.
Are we gonna do? Let's wrap it up.
Yeah, it would be nice. But
well, it's breathtaking to think about how much we do know. Like when we think about like how much do we have it dialed in? The beginning of the because I know we don't know the exact beginning of the universe, but we have it down to how many decimal points of the second?
Oh,
is
yeah.
it?
No, mathematically, at least.
Mm-hmm.
We can take things back to, just like the first even like couple of milliseconds after the Big Bang. The problem is there was a whole lot of stuff that happened up to that first couple of milliseconds.
Yeah.
And the universe grew to almost the size it is now within that very, very small time period. Inflation, the expansion of the universe was gigantic in the first the first few instants of space. And then, you take it to at about 100,000 years after the Big Bang is when matter could first start coming together and forming, where it wasn't just energy anymore. And, you've got the James Webb Space
100,000 years is all?
100,000 years.
That's fast.
Yes, it was fast. And you've got the James Webb Space Telescope trying to look farther and closer to that, because the James Webb Space Telescope is looking at spots in space where we couldn't see anything before and seeing things. And so at a particular point, they actually have the one James Webb Space Telescope finding is that the early galaxies seem to be bigger than were expected at that time. We're talking 100,000 years after the Big Bang is when, and then it's 100 million years after the Big Bang is when galaxies first started to be
That's
a thing.
Also
It's still
seems fast.
It's still fast, yeah.
Like 100 million years, that's nothing. I mean, we talk about evolution quite a bit on this show, and 100 million years doesn't always get that much stuff done in terms of life.
Oh, exactly. But 100 million years actually got to the point where the first stars are forming and everything like that. And so that's one of the things I've said a lot. When you start thinking about those time scales, most people can't really fathom 13.7, 13.8 billion years. There's no human frame of reference for that. But when you start thinking about it and you go like, oh. Astronomy is not a good hobby for those who are fascinated by mortality. And because the time scales that you're dealing with, our sun, 5 billion years, the Earth, 4.5 billion years. Those time scales don't mean anything to us until something triggers and it says, oh, I do kind of get this now. I know that this time scale is a little bit scary.
I love all the forced metaphors that we always feel like okay, take it. Say 100 years was a piece of paper and you stacked those. This is how far you would need to stack that to get to this. Always, all those metaphors always crack me up. It's like I don't know. I feel like I'm picturing 13.7 billion years as good as I'm ever going to. You can give me all the metaphors in the world, and it's like, all right, I guess I have as good of an idea as I'm ever going to have, probably.
That's the thing about the human brain as well.
Yeah.
And you know this from all of the biology that you're interested in, is that the human brain, the way we perceive things, is almost always in relation to other things.
Yeah.
So like when we're looking at the stars in the sky, on a good clear night, you go outside, nearly all the stars tend to look whitish. I mean, they really do. But then you'll occasionally see like Betelgeuse in Orion, or you'll see Mars out there, which Mars is actually out there tonight.
I didn't know there was a celestial body named Betelgeuse.
Yeah, that's Orion's shoulder star. Betelgeuse, a rough translation is armpit,
Okay.
but it's a very rough translation, but it's accurate. Betelgeuse is a star that could possibly blow up at just about any time.
Really?
It's one of those that could go supernova. I mean, it could have already happened, and we haven't seen it yet, or it could still be another 10, 15, 20,000 years, or it could
Is this
even be
another
longer.
thing I get to worry about?
Oh, no.
Can I add this to my list of...
Don't worry.
I don't have we're not just going to be shredded into nothingness by this...
1,300 light years, 1,300, 1,600, yeah, it's a long ways away.
Okay.
And so if it does go supernova, the reality is our atmosphere will protect us pretty well.
Okay.
And we're not going to get hit by a huge amount of radiation, just because a very tiny bit.
Radiation.
But we're hit by radiation all the time anyway.
Right,
So, our bodies are used to it. It's not that big of a deal.
Okay.
But
Not worried about Beetlejuice.
No, don't
Found
worry
out, that
about
was a
it.
whole roller coaster ride that I just went on with Beetlejuice.
Bunny
Went from
Hills.
not knowing what it was to feeling like a fool for not knowing it was Orion's armpit, to thinking that we are all going to possibly be obliterated at any moment, to being like, it's all going to be okay.
Probably okay.
Sorry, I hate to go off on too much of a tangent, but what do you think about these constellations? They're a little shaky.
Constellations are a very handy tool.
Okay.
But constellations have nothing to do with reality, except in a classification scheme for us.
I mean, I get that I mean, there's insects that navigate by starlight and are able to identify certain stars and things to navigate their way around. And I get how I'm sure there's all sorts of creatures in the world and fish and everything else, and so it makes sense that primates like us that really got wandering about would really develop this instinct to navigate by the stars, and obviously we learn well by constructing sometimes rather insane metaphors. We're storytelling apes, and so like as kind of a mnemonic device and everything, you can. But I get all that, but boy, like I just went to 2 days ago. Speaking of Area 15, I went to the Illuminarium there. And they have the space. Have you been in there yet?
I have not been in that one.
You
I've been in a different one. I saw
It's cool.
the Picasso. There was a Picasso exhibit one. I know it's a little different, but
the Picasso one was like. It was okay.
Yeah.
It was. I want to see like a Salvador Dali one or something like that.
the melting clocks would probably lend itself very well to that.
Yeah, the Picasso seemed like it was fine. It was fine. It's worth going. I just the lower part. Same with, and I must say in all honesty, I think I'm going to go to the wildlife one next week. But the Illuminarium, it's a really cool space. But they have this space program in there, and there's some really cool stuff. They have projections on the floor. You'll appreciate it as someone into projectors, and then you like step on like asteroids and they shatter and stuff like that. Yeah, they got a lot of fun stuff in there. But they had a part where they put up all of a bunch of the like greatest hits constellations and everything, and my God, you look at these things, or you fire up your phone and do one of the constellation apps, and I'm like, is that a bison though? Like I don't. That's like
You joke about the
3
bison.
stars and
Yeah.
is there a bison? I don't even know if there's a bison.
I had when I was at the planetarium I was at in Texas. There was a gentleman who asked me if I could create a bison asterism that he wanted.
Asterism.
Okay, well, we'll give you another definition here. So, the Big Dipper, most people think of as a constellation, but the Big Dipper is not actually a constellation. The Big Dipper.
You are just shattering.
See, you should have had an astronomer on sooner.
I know. I'm a fool.
But the Big Dipper is not a constellation. It's actually an asterism. An asterism is a piece of a constellation that has an identity of its own, or of several constellations that kind of have their own identity put. So the Big Dipper is actually kind of the flank and the tail of the Great Bear Ursa Major, that constellation. So I had a guy who actually asked me if I could create a bison asterism in the sky that would be available in the sky during this particular time.
Should have asked me. I can connect the dots and make it.
And I did. I connected the dots using parts of Ophiuchus and Sagittarius because he wanted it visible in September and everything like that. And all of the stars were magnitude 4. In a dark sky, you can see stars down to about magnitude 6.
Has anyone tried to make some boobs or something in constellations? Has there been any?
There's Virgo.
There has to be some.
Virgo the Virgin.
See, I knew it.
Yeah. So, but
it's probably the first thing they drew, I imagine.
It's a distinct possibility. Actually, no. Some of the first things were probably actually the Big Dipper.
Yeah. Well, that's because that's the. Pointing at the North Star, right?
Exactly.
And see the Dipper. Okay, I'll give you the. You look at the Dipper. I'm like, okay.
Yeah.
All right. I mean, a lot of things can look like a ladle.
Exactly.
But I'll give you the Big Dipper.
Yeah.
But any of the other ones? Are there any? Okay.
Orion does actually look like a person to a certain extent when you really look at it. Orion with the shoulder stars.
I'll look harder. That's a bold stance.
I mean,
but
no head. Really, think of it more like the tunic that would have been worn at the time.
Belt and
the belt and everything like that. So yeah. So I'm trying to think. The ones that, Sagittarius is supposed to be an archer, but of course most people refer to that asterism is the teapot. So when you see Sagittarius, the brightest stars form what we refer to as the teapot. There's more to it than that. For the constellation Sagittarius,
there must have been a lot of bickering.
Oh, I'm sure. Now, that's actually one of the things. The International Astronomical Union was actually formed to standardize the constellations.
When was that formed?
It was over 100 years ago.
What's
It was
the
right
name
around
of this organization?
The International Astronomical Union. And so they were brought together originally to standardize the constellations. And so they came up and using Greek and Roman and then Southern Hemisphere cultures and basically just a lot of different cultures.
Who was picked for it? Was this like a United Nations thing, or did one country?
It was pre-United Nations. This was scientists who got together.
But I mean, scientists from around the world, or did one country just?
It was supposed to be from around the world, and I think it actually was a fairly worldwide. I'm not 100% certain.
I just want to be fair with our constellations.
I do believe that it was probably through Harvard. Because Harvard, of course, at the time was one of the driving forces for astronomy and everything. I don't know for certain. That's one of the things. But if I had to venture a guess, I would say that the folks at Harvard tried to get everybody together to do this.
So they got people together, and then people agreed. They were like, absolutely.
They standardized.
That looks like a bow. And
yep. They standardized the constellations. But
I don't see it.
It wasn't really about what the picture was.
Okay.
What it was they took the pictures, the dot-to-dots that people had used, and then they basically just said, okay, well, we're going to draw borders around these. And so that part of the sky is going to be known as the Orion portion of the sky. And then that portion of the sky is going to be the Ursa Major portion. And that portion is going to be Draco's portion. And that portion will be Virgo. And that one's Cancer. And, all of those. So they drew borders as well. So that everything fit together like a puzzle. So that every part of the sky was considered a part of a constellation. It was about standardizing designations of stars so that you would start with the brightest star in a constellation area, and that would be known as alpha whatever of that constellation. And then beta of that constellation was the second brightest. So they used it as a cataloging tool. And when they standardized them.
That's all logical and it makes sense. It frustrates me as a comedian wanting to make fun of the...
Yeah. Well, and up until that point, it was just the mythology of it. It was just people telling the stories about the stars because they didn't really understand or know what they were. And so that made it familiar. And how humanity, the great apes, we have in our storytelling, we want things to be familiar. We don't want things to be scary. And so that was really the driving force behind the mythology of constellations. It was to essentially make the nighttime less scary by having these stories.
I mean, it must have had a fair amount to do with navigation at some period of time. Probably once there were more maps and more cities and more of the Earth was explored. Maybe the utility of those kind of shifted a little bit. But
you're looking at like the 1500s, really.
Yeah.
You know, but and so what was then discovered is that basically you could figure out where you were in relation to, say, Greenwich, England. You could figure out where you were based on how high above the horizon the North Star was. So you could say, oh, I know I am at this line. If I was to follow this line and keep the North Star at that same height for me, if I was to follow that line, I would end up back at such and such a place.
Oh my God, my heart is racing right now. If I had to get to, I think I'm 10-15 minutes from Area 15 here at this Airbnb that I've been at for nearly 2 months. If I had to get there without a GPS, oh my God.
Yeah.
I would. You'd have to call it.
Yeah.
Like I'd probably.
Well, it probably wouldn't be so hard. You just walk that way until you hit Las Vegas Boulevard. Actually, you can't even walk that way until you hit Las Vegas Boulevard because that way's south. So you'd have to walk that way over.
I can't even. You're overestimating my navigational skills. I can't. Like, people are like, it frustrates me to know. People will be like, oh, just I'm on the north side of the building. I'm like,
oh yeah, sorry. That's
no.
Probably the way I was telling you things when I was telling you how to get to the planetarium.
Oh, not necessarily. It happens all the time to me. I'm like, oh, I forget. And then this sun goes, is it west that it says east? Like, I feel so dumb every time. And people used to have to identify so many different stars to be able to navigate.
Mm-hmm.
The spaces.
Sailors, the one nice thing about it is, out on their ships at that time period, no electric lights. They would have had lanterns, but they would have been able to see the stars. They would have seen a lot more stars than what we can see now. And it would have been a little bit easier in that respect, at least. Mm-hmm. But yeah, no. And then the invention of the astrolabe, which was actually useful in determining exactly how high above the horizon a particular star was.
What's
what
an
angle.
astrolabe?
Basically, think of it as a little telescope without any lenses that you would look through and sight the star, and then it would have a hanging thing that you could then determine the angle above the horizon. And that actually was one of the things that really helped with navigation when they figured out how to do that sort of thing. And then, the reality
That's really
is...
interesting.
Oh, yeah. Human ingenuity really knows no bounds. Because, well, first of all, humans tend to come up with things to make life easier. That's always the case. We try to make our lives easier. And so in order to actually, be out sailing on the ocean, these things made life easier. If you knew where you were a lot better off. Mm-hmm. And so a lot of that development, in the, 1500s, 1600s, 1700s, as everything ramped up for taking those long voyages across and everything, it was definitely necessary. A lot of people didn't end up where they thought they were going to.
Yeah, I'm sure. All right. Well, going back to, I don't know what you're.
Tangential's fine with me.
Yeah.
I'll go off on any tangent.
Oh no, I know. I wasn't expecting that tangent to go so long. So now I don't know if I want to. Well, let's go back to the start of the universe again. So, because I would like to, walk me through. You don't need to give me the textbook run through. I want to know, in your mind, after studying this, after running a planetarium, after I'm sure answering a zillion questions from little kids to adults.
Mm-hmm.
When you kind of close your eyes and picture the early history of the universe, what are a lot of those? How does that play out? What are a lot of those key moments?
The milestones.
Yeah, the milestones.
Well, okay, so, the first milestone obviously is just the start, the Big Bang, the big whatever people want to call it. All sorts of jokes about that. That milestone, 13.8 billion years ago, is the beginning of it all. And then the next milestone, of course, is the expansion. The universe rapidly, very rapidly, becoming almost the size it is today. Granted, it's still expanding, but you're almost before time was relevant, the universe was as big as it is practically today, save for the slowed down expansion. Next milestone, the energy cools enough so that atoms can actually form. And we're talking about, the first protons and electrons, so, like the primordial hydrogen and helium that would have come together at that point. And so after that, the next milestone is the first star. There has to be a first star. There has to be a star that that emitted its light first. Mm-hmm. But the reality is, it probably was a humongous thing. It was probably extremely large. And when it coalesced and came together so that hydrogen mostly started to change into helium at the center by being squished together and the temperature being so high that it burned through that hydrogen so quickly, turned it all into helium very quickly. And then that helium, because it was such a large star, it was able to compress, and the helium turns into carbon and oxygen. And so you probably have a lot of stars that are forming all at roughly the same time. And probably a lot of these stars became what was more than likely the center of the galaxies that we see today in a lot of cases. And they might not have lasted very long because they were so large. They grew so quickly, and their cores were changed to iron so quickly that when they exploded and threw that material out into the universe, then the next could go on. So, and then, once you have stars, you have the galaxies that form. It was thought originally smaller galaxies formed and then merged and became bigger galaxies. And so, you're looking at, the 13.5 billion years ago now. So you're still 300 million years.
Yeah.
And so, that to me takes us almost to the universe we see today. Gigantic stars that actually threw this material out into the universe and then led to us. Led to second generation stars, third generation stars, fourth generation stars that had higher amounts of more than just hydrogen and helium. And the material left over in those clouds around them to start forming those planets and things like that around as well. Just nuts to think about.
So what is kind of, if as we explore more, we're all a bit familiar with our universe in the way planets in our universe look. I was at the planetarium, and the thing outside that had all of the
the exoplanets.
The exoplanets. What are some of the most vastly different areas of the universe from what we're familiar with?
There's not a whole lot that are vastly different at this point. There are some. And it mostly stems from what we know about our solar system to what we're finding about planets with other solar systems out there. And so, like our solar system, we have the 4 inner planets, which are all rocky bodies with iron and everything like that. And then we have the 4 gas giant planets, which are, they have large amounts of hydrogen and helium also, and they don't have a solid surface. And then we've got the icy rocky bodies that are out, like Pluto is one of them and everything. And so a lot of scientists thought, well, if we find other planets out there, we're going to find things very similar to what we have here. We're going to find the small Rockies. We're going to find the larger. And what they've started finding is there are things that are in between. Earth and Venus are roughly the same size. We're the biggest of the Rockies that are in the closer in. And Neptune and Uranus are 4 times the size of Earth, roughly. So they're starting to find things that are like, oh, well, there's some stuff that might be, there's some planets out there that are like twice the mass of Earth. So are they actually hydrogen and helium, or are they more rocky, or is there some sort of even a hybrid there? So we're finding that the sizes of planets runs the whole gambit. It's one of those things that really just if you get up to more than about 10 times the size of Jupiter, you're getting into failed star category. And they call those brown dwarfs. And so a little bit bigger than that, and they can become stars. So up to about 10 times the size of Jupiter.
Sorry, when you say failed star, what's
So brown dwarfs are large enough that some amount of fusion probably occurred in their core, turning some of the hydrogen into helium, but there wasn't enough mass, pressure, temperature to sustain. And so, or there might actually be a very low level of fusion going on fairly constantly. And so those are brown dwarfs. They are, anywhere from about 10 times the mass of Jupiter up to maybe, not real sure. But so yeah, they just never quite made it.
Sad.
Yeah.
What a label to give them too. These poor.
Yeah.
Just call them failures.
Well, a lot of times they get referred to as brown dwarfs, but even that.
So much better.
Yeah, not really that much better.
And what's so? It's so fascinating that we can mathematically sort out. I say we like it's like you and me doing it. Mathematically figure out, kind of rewind the clock and see where all of this came from, all the way down to milliseconds after the Big Bang. What about the future? What does the future of our solar system look like?
Oh, the future of our solar system, we've got about 5 billion more years.
That's not bad.
No, it's not bad.
So we're having like a midlife crisis right now.
It's a midlife crisis. Okay. What's going to eventually happen with our sun is it's going to start to run out of hydrogen at the core. The hydrogen's being converted into helium. Kind of talked about that a little bit. And so what's going to happen is when that process stops, then it's going to start to shrink a little bit. The sun is. And so it's going to contract, it's going to come in, and that contraction is going to lead to the temperature going up even higher in the center. Right now it's about 27 million degrees in the center of the sun. So that temperature is going to rise up higher, and it's going to allow the helium, which is the sun's core is going to be mostly helium at that point. The helium will be able to turn into carbon and oxygen through the fusion process. That releases energy also. So the sun is going to, then it will expand and it will grow and it will swallow Mercury, Venus, Earth, and probably Mars, or at least go pretty much out to Mars. And so at that point, we're gone. That process will basically burn off the atmosphere. The oceans will go away. And if there are humans still on the Earth when that happens, they're toast. At that point, if we haven't figured out how to get off, we don't deserve to.
How long do we have before
5
that?
billion years, roughly.
Yeah, I mean,
We won't be here in 5 billion years. Whether it's by choice or by accident, we won't be here in 5 billion years.
Right.
So those, as the sun expands, those outer layers will just kind of keep poofing off out into space, and what's left behind will be a core of carbon and oxygen, a very rigid lattice core of carbon and oxygen, which will literally be an Earth-sized diamond in the sky. So Twinkle Twinkle Little Star was right all along. Like a diamond in the sky. That's kind of what they can end up being, those carbon and oxygen cores. That's a small star, like our sun. Our sun is kind of a smallish medium star. And so it will become a white dwarf where nothing will be happening, but that heat will just radiate until it finally cools off to ambient temperature in the background. Bigger stars, they'll explode. They actually go through that process, carbon and oxygen, and then they keep going higher and higher because that pressure is enough to push, because they're so large, it pushes more and more together until it reaches iron. And I mentioned that earlier, but once a core of a star becomes solid iron, then fusion stops. And the star contracts rapidly, and the shock wave from that rapid contraction blows the outer layers out, and you get a supernova at that point, which seeds material out into the universe.
Are there many collisions going on out there? Is it because you mentioned that there's all of this expansion, and eventually everything's going to get so far apart that there won't be anything at all. But in the meantime, are there any galaxies that I should be keeping my eye out for crashing into ours or anything like that?
Of course, yeah. In 2 billion years, Andromeda is going to be hitting us.
What's Andromeda?
The Andromeda galaxy is the largest galaxy that is close to our own. It is right now about 2 million light years away. And it's in the constellation of Andromeda. It's actually visible in dark skies with just your eyes. It kind of appears as a fuzzy patch. But it's a spiral galaxy, probably actually a little bit bigger than the Milky Way. Probably has somewhere between 400 billion and 500 billion stars. The Milky Way is probably 200 billion to 300 billion stars in it.
Okay.
But
almost double the size?
Yeah, almost double.
Okay.
Maybe not quite. It might be the 450 to 300 kind of a thing, but
I won't hold you to it.
Yeah, estimates are
Yeah.
they're touchy situations when it comes to all of that. But we will eventually merge with Andromeda, and there will be a few stars that do collide. The just on average because of how many there are, but for the most part, what'll collide is the dust.
Wait, how many stars in each again?
Probably around 200 to 300 billion in the Milky Way, and about 400 to 500 billion in the
and
Andromeda.
they're just going to merge, and those stars.
Yeah, they'll pass like ships in the night.
That's just how not dense these galaxies are.
Exactly.
Wow.
The nearest star to our sun right now is about 25 trillion miles away.
Yeah, that's a lot of empty space to move another star through.
A lot of empty space.
Okay.
But the gas and dust that's there will collide. And so when the Milky Way and Andromeda galaxies merge, that gas and dust is going to collide. That's going to trigger new star formation.
More stars.
So by the time the merger is complete, probably we'll see a large elliptical galaxy with not much gas and dust left that probably has upwards of 1 trillion stars by the time it's done. So that's about 2-something billion years from now that we start the merger.
Wow.
And we can actually see galactic mergers happening. We can see about 2 trillion galaxies in the sky.
We can see 2 trillion galaxies?
Yeah, and that estimate actually went up in the last 10 years. NASA used to estimate that we could see about 200 billion galaxies.
Wow.
In the observable universe. But
So we 10 times it.
we 10 times it, yeah.
Wow.
And some of that is, Hubble, and some of that is James Webb now and everything. But yeah, so there's at least 2 trillion galaxies out there.
Who's counting these puppies?
Just a density, density calculation.
Yeah, that makes a little more sense than to check off by finger each region.
When you take the Hubble telescope and it's looking at an area of sky that never had seen galaxies in, and then all of a sudden there's like 6 million galaxies that had never been seen before. The estimates could go up quite a bit.
and in those galaxies, going back to something you said earlier, this is like sort of the norm-ish, like what we're familiar with.
Yeah.
And this is because we can kind of we can judge based on the light being given off by a star. We can kind of see it's what it's made out of, right?
Yep. Spectral analysis.
And so well, that makes the different ones even more peculiar. Like, how does it happen when there's these outliers?
Well, so that actually the classification of stars actually goes back to Harvard as well. And at the time, they hired calculators. I know it sounds funny, but they hired women to actually look through all this stuff, and they referred to them as calculators and computers. And so one of the women,
was this?
1900, around 1900.
Okay.
Or so one of those women, Annie Jump Cannon, actually classified about 300,000 stars by herself. She separated the spectral analysis that Harvard had been taking of all these different stars. And
hold on. Wait. I don't understand. What's this process like?
At the time, they would take a picture of the spectrum. So they would run the starlight through a telescope, run it through a prism, and then photograph the spectrum that was produced. And so they had all of these spectral pictures that had been taken. And so Annie Jump Cannon took and started separating the different stars, the spectral pictures by how complicated the spectra were. And so she designated the ones with the least complicated spectrums were A's. B's were the second, were the next most complicated. C's, D. She did it just based on an alphabetical scale. And so what she started to find was that as she was putting more and more together, the scale...
More and more? She did 300,000? I don't understand that.
Well,
how do you... What?
Tedious work, and she just... It was something that she actually enjoyed doing, but she also... she was very good at it. She just loved doing it, and so her classifications of stars, there were ones that for the most part saw that most of the stars fit into these categories.
Okay.
And so the letters that are mostly left over now are O, B, A, F, G, K, and M, and then R, S, or R, N, and S. So that batch was what most of the stars fell into as far as their spectrum was concerned. And they didn't realize it at the time, but now with the OBAFGKM, that's actually a temperature scale as well. O stars are the hottest stars, and the K and M stars are the least hot stars. And so it's a temperature scale. It is a spectral scale, but so most of the stars can be classified in those classifications, and that's what we see. So, but yeah, it's crazy. And for the longest time, she didn't get the credit she deserved for what she had done. And it's really probably just in like the last 30 or 40 years that she's really, been given a lot more credit for what she did.
No one was like, there is some crazy lady that has classified 300,000 of these things. We got to give her an award or something.
Yeah, it should have been done. So
that's insane.
Yeah.
If my job was just to count to 300,000, like,
you'd win an award.
I would win an award.
You
for
would
that.
want one, yeah.
Yeah.
So yeah, it's astronomy.
I still don't understand.
It's full of these crazy stories like that. There's a lot of people there are a lot of women who came up with ideas that were co-opted by male astronomers as well. And the male astronomers won the awards, and the women are just now being recognized that, oh, hey, maybe this is the person who should have won the award.
Yeah.
So
well, that's happened. I think the first vaccine was introduced by a female, but no one took it seriously until a guy rebranded it.
Yeah.
Not good with names, but that's the gist of what happened. Yeah. Well, anyway, what as we start wrapping up, what about planetariums? There's so many planetariums around. When you reached out to me, the reason why I was so excited was because I'd been to a planetarium many times when I was a teenager and then in early 20s. Yeah, may have coincided with some of my weed smoking years.
You're not the only one.
No.
There's a lot of people who come in.
Yeah.
We're used to it.
Yeah, I'm sure. Well, you have a hell of a gift shop too. I got a space pen from my first space pen.
Yes.
How did I go? I went 42 years without a space pen.
Yeah.
It's crazy. But anyway, as we start wrapping up, what do you look forward to in advancements in planetariums and that sort of thing? Because we have this giant sphere opening up in the fall here in Vegas.
The Madison Sphere Garden as well, which a little bit of
got
consternation on my part. Hey,
you don't think you're going to be able to compete with the 12,000 seat?
Yeah, no, I can't compete with a 16K by 16K dome. But our planetarium, it's about time for an upgrade. It's much more intimate. We seat about 66 folks, and so, yeah, we need to do an upgrade in the planetarium, and so the biggest thing for me would be changing from our halogen projectors to laser projection.
Oh, nice.
The laser projectors last about 10 times longer. You don't have to replace the bulbs constantly. I go through a set of 4 bulbs every year for my 2 projectors, which take two bulbs each.
Are they higher quality and everything too? And then,
$600 a piece. So
I mean, just in terms of the picture, is the picture higher quality with the laser?
Well, yeah, the picture is definitely higher quality with the laser.
Yeah.
Brighter as well. That's one of the things that occasionally we have some issues with the brightness on the dome. I'd like to have it a little bit brighter, but there's not really much we can do about that. But if we go to the lasers, yeah, we'll be able to. And upgrade to maybe a 4K system as well. That would be nice. So that's in the future for us. I think some of the next steps that we're going to see are going to be, instead of projection up, you're going to actually see more of the LCD screens. Essentially, being, because you can have the flexible screens now, you can have the screens that bend and shape and everything like that. Our system, the company that makes our system, has an LCD screen in Salt Lake City that they have developed that can project their images that way. And so I think that we'll see some of that coming in the future, especially. Most planetariums will not be able to afford it.
Yeah.
a lot of us, we operate on a shoestring budget, but we
Get
we
out to the
by.
planetariums,
come on out to
guys.
the planetarium. Visit the Dale Etheridge Planetarium at the College of Southern Nevada on the North Las Vegas campus. We're just off of Cheyenne Avenue, and we're open on Friday and Saturday nights, 6, 7, and 8 o'clock shows. We open the telescopes after the 8 o'clock show, so we try and do a little bit of observing too, as long as it's clear outside, and give folks a chance to actually see some of the objects with their eyes.
Oh, I got to come and do that before I leave.
Yeah. And so, but that's, we've actually been really cloudy this spring here in Las Vegas. For a city that supposedly has 330 cloudless days a year, we've missed a lot of our astronomy viewing with the telescopes because we've gotten cloudy. I blame El Nino. It's we've got this the Pacific Ocean's nice and warm right now, so we're getting we're getting some clouds in the evening, but yeah, we open up the telescopes, come out, check out a show. We have our volunteer interns. They come out and they actually help with the shows, and they actually create their own star talks as well. So we show like a feature presentation, and then we do a little star talk that everybody kind of has made their own. So it's a lot of fun. Our interns are very, very fantastic.
Very cool. Well, I look forward to maybe we'll collaborate on a project of our own one of these days. One of the things we've been chatting about a little bit.
Yep.
And I have a lot to learn, but that seems like a fun thing to do. And yeah, thanks so much for joining me, Andrew.
I really enjoyed it. It's a lot of fun being able to come out and do something like this, and sometimes it's a lot of fun just to be able to go off on tangents too.
Oh, I love tangents.
Yeah, we joked about it being tangential physics when we were undergrads.
Yeah,
we always went off on our tangents.
Yeah, I love it. Well, thank you, listeners, for being such wonderful, curious people, and we'll talk with you more next episode.